All right, here's an example of a two-object system. We've got small m here, we've got a mass big M over here. It says here when the system in the diagram is released from rest, the 2.42 kilogram mass little m has an acceleration of 1.58 meters per second squared to the right. The surface and the pulley are frictionless. Want to figure out the tension in the connecting cord and the mass of big M. So the way we've started these is by drawing a force diagram for each object. So we'll go ahead and do that. Little m is going to have force of tension acting on it. Force of tension in this direction. We've got force normal acting up and the force of weight acting down. We can go ahead and figure up the weight for this. So let's go ahead and do that. It's 2.42 kilograms times 9.8, which is going to be equal to 23.7 newtons. What was it, 23.7? Yeah, 23.7. 23.7 newtons. Over here we've got little m, or excuse me, big M. We've got force of tension acting upward. And force of weight acting downward. We don't know this. We'll come back to it. Want to figure out the tension, so we want to figure out T. The other thing we've done is we've drawn a third force diagram in order to linearize this. It's what I call it. I don't know if there's a better word for it. Essentially what we do is we take and we've got big M, excuse me, little m over here, and then we pretend this pulley isn't here. All the pulley does is redirect force anyway. So it's the same force in this tension, this cord, the same tension force in this entire cord. So what we do is we just straighten it out and pretend it's, you know, the pulley is not there. There's big M. So what we wind up with is on this end we've got f of g for big M. So let's make that a big M. So we've got f of g for big M here, and then over here we've got nothing. There's nothing pulling in that direction. All right, so let's go ahead and see what we've got here. The next thing we do is we'd rotate it if we had it on a ramp. We don't. After that, we would, what the heck would we do? Evaluate the motion. We know that all of this whole thing is accelerating to the right. So acceleration is to the right at 1.58 meters per second squared. So, I guess what I could take a look at is an individual object, this force diagram here, because we do know that it's accelerating in that direction. So for in the x direction for just little m, since we have that kind of information for little m, in the x direction, sum of the forces is going to be equal to ma. So in the x direction, we've got f of t is going to be equal to ma. We know m, we know a, so we can find f of t. So f of t is going to be equal to m, which is 2.42 kilograms, times a, which is a positive 1.58 meters per second squared. So that gives us tension force of 2.42 times 1.58, 3.82 newtons. So that's the answer to part A. Part B asks what is mass big M? Okay, so let's go ahead and attack that. Uh, wow, what are we going to do here? So for part B, um, well, we know for the whole system, we know that sum of the forces is going to be equal to MA. So we've got F of G for the large mass, big M, is going to be equal to the mass of the system, which is going to be little m, plus big M times acceleration of the system. So let's go ahead and put some numbers in here, stuff we know. F of GM, we don't necessarily know any numbers here, but that's going to be equal to, if I were to figure it out, it'd be big M times the acceleration due to gravity, which is g. So I've got big M times g is going to be equal to little m plus big M times the acceleration of the system. So I can put in some numbers here. Let's do this. Let's go back. Little m is 2.42 plus big M, which I don't know, times A, which is going to be 1.58. 1.58 meters per second squared. It's kilograms. So G is 9.8, so let's go ahead and do this. So let's fix this up a bit. It's going to be 2.42 kilograms. And let's fix this up, because that's really going to be big M times 9.8 meters per, move it over a little bit. Big M times 9.8 meters per second squared. Now the thing is that going to be positive or negative? And it's going to be positive because that's pointed to the right. Okay, so let's go ahead and see what we can do here. We've got M times 9.8. It's going to be equal to 2.42 times 1.58. So I'm just going to distribute that 1.58 throughout. So it's 2.42 times 1.58, which is going to be equal to 3.82. So 3.82 plus 1.58 big M. So I'm going to subtract that over to the other side, and I get 9.8 M minus 1.58 M is equal to 3.82. So 9.8 minus 1.58. 9.8 minus 1.58 is going to be equal to 8.22. So I got 8.22 M is equal to 3.82. So that means that M, big M, has got to be equal to 3.82 divided by 8.22. So that's going to be 3.82 divided by 8.22, 0.465. So M is going to be equal to 0.465. It better come up in kilograms, and I'm just going to take a quick look at the units to make sure it would. Um, let's see here. I dropped the units here. So this first one, this would be in newtons. And then this is going to be meters per second squared. This would be meters per second squared. So when I subtract this over, this is going to wind up being in meters per second squared. This is in newtons still. So then I wind up with, let's go over here, I wind up with newtons. I'm going to go to the next page to just finish this up. I wind up with, oh, I got some room. Cool. Newtons divided by meters per second squared. Let's do that in a different color. There we go. Meters per second squared. So that means that this is a kilogram meter per second squared over a meter per second squared. So yeah, these guys cancel. I'm left with kilograms. So yes, it does come up to be in kilograms. Good. All right, so we've taken care of the question. A little bit of algebra there, but we've got it all.